proton equals 1.67262 times 10 to the power minus 27 kg, and that for a neutron equals 1.67493 times 10 to the power minus 27 kgs. Now, if you look closely at these two numbers at the bottom, you'll notice the mass of proton and the mass of a neutron are almost the same. Wait, one more thing to notice here. If you look at the mass of electron here, look at the power of 10. What do you see? You see a minus 31, right? All right. While the other two values, they have minus 27. That shows how the mass of a proton or a neutron is much, much higher compared to that of an electron. In fact, the mass of a proton or a neutron is 1837, or almost 2000 times that of the mass of an electron. Here, I have 1 kilogram of rice. And now, if I remove 1 or 2 rice grains from it, and I ask you how many grams of rice I have, you'll still say approximately 1 kilogram, right? Similarly, the mass of electrons is so much smaller than the mass of neutrons and protons. Electrons don't add much to the mass of an atom. So the mass of electrons is neglected while calculating the mass of an atom. Look, this was the expression we arrived at earlier. Since we neglect the mass of electrons, we can remove that part, right? And this becomes the new expression of the mass of an atom. Also, as both neutrons and protons form the nucleus, they are collectively called as nucleons. And since the mass of protons and neutrons are almost the same, we can replace both mass of protons and mass of neutrons here with mass of nucleons. So the expression here can be further modified to Np plus Nn, number of proton, number of neutron, summed together, multiplied with mass of a nucleon. All right. The value of this mass of nucleon is taken as approximately 1.67 times 10 to the power minus 27 kilograms, or 1.67 times 10 to the power minus 24 grams. This expression is set to give you the mass of an atom in grams or kgs. Except there's one more thing. The part inside the bracket, Np plus Nn, this has another name, and the name is mass number. This name can be justified by a point we discussed a while ago. Remember, we neglected the mass of electrons while calculating the mass of an atom. So in a way, we can say that the mass of an atom almost equals the mass of all the nucleons. That is, the mass of all the protons and neutrons combined. As a result, the sum of the number of protons and neutrons is called as the mass number. It's denoted by capital A, and the mass number A times the mass of a nucleon approximately gives us the mass of an atom. Mass numbers of most elements can be guessed from the periodic table as well. The mass number data is given along with the symbol, and when this number is very close to a whole number, that whole number itself becomes our mass number. Now, of course, we'll be seeing more details about this a little ahead in the chapter, but for now, this much is enough. Mass number of carbon, sulfur, and helium are 12, 32, and 4. Let's find their masses. As the mass number of carbon is 12, the mass of a carbon atom would be approximately 12 times this unusual number, 1.67 times 10 to the power minus 24 grams. Similarly, masses of sulfur and helium atoms would be approximately 32 times this number and 4 times this number, respectively. Now, if you look at these masses of these three atoms, what do we see? We see multiplication involving this gigantic number. We don't want to do that. Thankfully, we have another unit that can be used to express the mass of atoms. And this will help us avoid this weird multiplication. That unit is the atomic mass unit, abbreviated as AMU. The value of AMU is this unusual number that we had to multiply every single time. That is 1.67 times 10 to the power minus 24 grams. Okay, this is equal to 1 AMU. Now, while AMU is the name that is generally used, there are a couple of other names as well. One of them is Unified Atomic Mass Unit, or U in short. This is one of the names that IUPAC has given. They also called the same unit as Dalton, or DA in short. This was to honor John Dalton, who proposed the atomic theory. Also, don't worry about which one to use. Whether it's AMU or U or Dalton, they can all be used interchangeably to express the mass of an atom. Alright, now let's find the masses of the atoms that we discussed just before, but in AMU this time. Alright, let's first consider carbon. We found the mass of a C12 atom as 12 times this unusual number, 1.67 10 to the power minus 24 grams, right? But this number is equal to the value of 1 AMU. Is that not? So we can replace this expression with the unit AMU, and the mass of the atom here becomes 12 AMU. So in conclusion, all we have to do is to take the mass number of carbon, that is 12, and put AMU after it. Correct? Alright, this is easy. Similarly, the mass of a sulfur atom would be mass number 32, so 32 AMU. We can also say 32U or 32 Dalton. Similarly, the mass of a helium atom can also be written as 4U or 4Da or 4 AMU. Also, similar to how we had a formula to calculate the mass of an atom in grams, we can have another formula here, but this time with AMU as the unit. So, behold, mass of an atom equals capital A, the mass number multiplied with AMU. Alright, so this was about atomic mass. Now, similar to this, that is the mass of an atom, we also have a new term, another term which we call as molecular mass. Molecular mass is a term used to describe the mass of a molecule of a given compound. Molecular mass is also expressed in AMU or U or Da. Now, how do we calculate the mass of a molecule? Or in other words, molecular mass? Well, molecules are made up of atoms. So if you add up the mass of all the atoms in a molecule, you'll get the mass of that molecule. Let's take CO2 as an example. The mass number of carbon is 12. So the atomic mass of carbon becomes 12 AMU. And the mass number of oxygen is 16. So its atomic mass becomes 16 AMU. But wait, in CO2, in a single CO2 molecule, there are 2 oxygen atoms. So we need to take twice of this value. That is 32. The molecular mass of CO2 turns out to be 44 AMU. Now, instead of writing AMU so many times, we can just add up the mass number of various elements and then add an EMU after it. Let's find the molecular mass of some compounds to get a hang of this. First one is PH3. All right, let's see where PH3, oh yeah, there it is, right? Okay, see this superscript? Its mass number as a result turns out to be 31. All right, and the mass number of hydrogen, well, we know that is 1. But there are 3 hydrogen atoms in addition to the 1 phosphorus atom. So the total mass number of PH3 would be 31 plus 3 times 1, so total of 34. To calculate the molecular mass, we just put an AMU at the end, and as a result, we get the value of molecular mass of PH3 as 34 AMU. All right, let's take SO2 next. Here it is. So what do we see? The mass number of sulfur is for twice of 6. Just apply AMU after it again, just like we did for atomic mass. All right, so let's bring all the values over here. Okay. And in the case of atomic mass, total mass number or molecular mass equals A total AMU. And we know AMU equals, and you might, which are industrially and competitive exams. All right. Oh, wait. One more thing I forgot to mention. Remember, we took the approximate value of AMU as 1.67 times 10 to the power minus 24 grams for the ease of understanding, right? There is something interesting behind the history of AMU and its actual value. Every time we number tells us the how much or the how many, and the unit completes the given information. The unit, in a way, provides an identity to the number. Without either of these, our communication will be incomplete and irrelevant. Let's say my mass is 80 kgs. In other words, I am 80 times heavier as compared to 1 kg. This kg here is the reference based on which I'm expressing my weight to you as the reference to express the mass of substances. A similar concept being the mass number of the element. But before the atomic mass, abbreviated as RAM. Now the RAM of carbon, for example, was calculated and it came out to be equal to 11.91 or approximately 12. Similarly, for helium, the value of RAM turned out to be 3.97 or approximately 4. But now that we know about the conceptual idea behind AMU, we can also say that the atomic mass of an element can be expressed as RAM followed by AMU. Take carbon, for example. Its RAM value is 12. Just like we talked about, we have stated the definition of RAM. Defining something similar for molecules is not that difficult. The next term on the agenda is relative molecular mass. Now, molecular mass is also best expressed in AMU or U or DA. The DA is for Dalton. Okay, so it makes sense that 1/12 the mass of a carbon-12 atom is taken as a reference unit for the mass of molecules as well. And therefore, RMM, the abbreviation for relative molecular mass, becomes the ratio of the molecular mass of a compound to 1/12 the mass of a carbon-12 atom. Also, as we already saw before, atomic mass is the mass number of an element followed by the unit AMU. In short, we can say it as AMU. Similarly, molecular mass is calculated as total mass number followed by A, or in short, A total A. When we divide these two by 1/12 the mass of a C12 atom, which is equals to 1 AMU, we'll be left with, think about it, In the case of atoms, A, and in the case of molecules, A. 14 and 28 both come in the table of 7. So 1 by 7 equals 0.1428. This number you should always remember. With that, what can we say? We can say that, the value is coming out to be 14.28 percentage. And obviously this is more because 16 is more than 14. And with that, we can easily say that this question over here has been concluded. And option C, C for Calcutta over here is turning out to be the correct response. Alright people, let's take a look at this question. What is this question trying to say? We have 20 molecules of SO3, right? And the question is saying how many molecules of oxygen will weigh the same? That is what we have to find out over here. Alright, so let's begin. First of all, what do we have, right? Okay, let's proceed with this thing. So we have SO3, correct? What is the weight of one molecule of SO3, right? So essentially, if I have to talk about the molecular mass over here, that will turn out to be what? We will have 32 for sulfur and we will have 48 for oxygen over there. And obviously, we are dealing with AMU because we are dealing with molecular mass. Same calculation if we do with oxygen. Now tell me whether it should be O or whether it should be O2. What will it be? Shall I remove the 2 from here or I'll keep the 2 from here in the subscript of O? Well, the question is talking about, as you can see in the question, molecules of oxygen. So we are definitely talking about O2 and not O, because then the question needs to say atoms of oxygen, right? The question is saying molecules of oxygen. It is an indirect, smart, tricky way to tell us that the question is talking indeed about O2 and not O. Now, what will be the molecular mass value for this one here? Well, simply put, we will have 16 times 2 AMU. And yeah, 32 AMU turns out to be our answer. What is the total coming out to be in the other case? What do we have over here? We have 80 AMU over here. Okay, now how do we deal with this? Okay, so this is saying 20 molecules of SO3. So 20 times 80 AMU should be equal to, in terms of its weight, with X molecules of each oxygen molecule weighing 32 AMU. Now, if we solve these things out, what does this become? This becomes essentially what? 1600. Then this 1600 becomes 100 and we have a 2 here and the AMU also gets cancelled out. So we have our question solved right on a single page over here per se. Pretty easy question. The value here is turning out to be 50. That is B for Bangalore is indeed turning out to be the correct response for this question. Alright people, let's take a look at this question. What do we have? It's saying cisplatin, an anti-cancer drug. Oh my god, what's that, sir? This question is difficult. Don't worry, right? Okay, this is the trick of the examiner to drop complex words and new words which you might not be aware of, just to, distract you or make you afraid or, make you do mistakes. Don't do that, right? We are smart people. So what do we have over here? Cisplatin, an anti-cancer drug, has the molecular formula PT. Oh my god, sir, PT. We have not dealt with PT. What is PT, sir? Don't worry, it's mentioned over there. Platinum, and the value also has been mentioned in the question. Don't worry, yeah? So, platinum is there, then PT, NH3 whole twice, Cl2 is there. What is the mass in grams of one molecule? Oh, this is a simple question, right? Okay, because we only have to calculate the molecular mass. Okay. Mass of one molecule in grams of molecular mass is one and the same thing, right? Just that because it is asking in grams, we might have to do some mathematical calculations.
But yeah, that's okay. So what else do we have over here? We have that, the mass numbers of PT, hydrogen, nitrogen and chlorine has been provided. So you know what, let's do one thing. First, let's try and calculate this value in AMU. Yeah. So if I go about calculating the molecular mass over here, what do I get? I get that, I have one PT atom over here in one molecule, correct? Then what do I have? I then have NH3. So NH3 will be essentially what?